So what I'm going to talk about now is I'm going to be talking about conservative vector fields and potential functions. Conservative vector fields and potential functions are very crucial to understanding and being able to do the fundamental theorem of line integrals. Once we kind of understand how these vector fields work and their relationship to these things called the potential function, and how do we retrieve potential functions, the fundamental theorem of line integrals ends up becoming, fairly simple, and in fact becomes very, very handy to work with to go out and do integration, because it makes everything a lot easier. So we want to start out talking about these conservative vector fields and their associated potential functions. So in our work on vector fields, we stated that for a vector field f to be conservative, there needs to be a function phi, and phi is this, such that del phi is equal to f. Okay? And so we had a test, and we had this test for a conservative vector field. So one of the things that we do know is we know that we've got this thing called the cross partial property of conservative vector fields. So if we've got f as a vector field in 2 or 3 dimensions, such that the component functions of f have continuous second order mixed partial derivatives on the domain of f, if f of x equals pq, right? So p of xy, q of xy, and those we'll talk about. Those are 2 functions that make up our vector field. Is a conservative vector field in R2, then dp dy is equal to dq dx. Okay, and conservatively, consequently, if we have it in 3 dimensions, like we have a p, q, and r is a conservative vector field in R3, then dp dy is equal to dq dx, dq dz is equal to dr dy, and dr dx is equal to dp dz. Okay, so basically what this is saying is it's saying, okay, let's imagine that I have, right, I've got my vector field f, okay? F is equal to p of xy, q of xy, okay? And we'll just do this in 2 dimensions right now, okay? This, right, should be, if we actually do have our phi, this should be phi of x, right? Because theoretically, we want to know whether or not we're actually going to get del dot phi. Okay, so this should be phi of x. This should be phi y. They should be coming from the same function. That same function is that function phi, which is our potential function. We want to know whether or not we actually are getting partials from the same function. Okay, so how do we know that that's the case? Well, if this is actually phi x and this is phi y, then we also know, right, if this is true, that means we get phi xy equals phi yx. Okay, that if we actually take the mixed partials, right, in different orders, those two should end up being the same. That's actually a rule of partial derivatives. We know that that's the case. You take the mixed partials, right, and it doesn't matter which order that you take them in, you're going to get the same value. Okay, so basically what this is saying is we've got a test for determining whether or not we have a conservative vector field. So let's take an example. Let's suppose that we have f of xy equals yi minus x squared yj. And I want to know whether or not f is actually conservative. Okay, so what I'm going to do is I'm actually going to say, okay, if f is conservative, then this is going to be phi x, this is going to be phi y, okay? And conversely, we're going to see it also written as, this will be called q, and this is going to be called p, all right? But right now, I'm just trying to connect the values inside of our vector field, right, to this potential function phi, okay? So if I take, so what I need to do now, since this is phi x, I need to find the derivative with respect to y. So d dy of y, okay, that's the function, is just going to equal 1. And then I'm going to go over here to the other one, and I'm going to take the derivative with respect to x. So this is going to be d dx, right, or del dx of x squared y, and that's going to equal 2xy. 2xy does not equal 1, so f is not conservative. We can't find that potential function. That's what we're going to say right now. I can't find it. I won't be able to find it. It's not conservative. Let's consider this one. Take another example. Is f conservative? So now we have f of xy equal to 2xy cubed, and then 3x squared y squared plus cosine y. So now we're going to use our notation, our P and Q notation. P of xy is thus going to equal 2xy cubed, and Q of xy is going to equal 3x squared y squared plus cosine y. We're going to take the partial with respect to y. We're going to find p sub y. And so p sub y is going to end up giving me 6x y squared. And then I have q sub x. So q is like your derivative with respect to y. So we're going to take q sub x, and that's going to then give me 6x y squared as well, when we take its partial with respect to x. Since py equals qx, the vector field f is conservative. Now we need to make a determination about this function. Notice that this function, or this vector field, excuse me, is in terms of x, y, and z. So we're going to have a p, q, and an r this time. So our p is going to be this first one. It's basically our x coordinate. It's going to be negative 1 over y. Our q is going to end up equaling x over y squared. And our r now is going to be, for our z component, it's going to be 2z minus 1. Okay? And if we were really, writing this out, we'd call it p of x, y, z, because it's a function of x and y and z, just to remember. Now, what we're going to need to do, since this is like our x1, our x component, we're going to need to find py and pz. So py is the derivative of negative 1 over y with respect to y, and that ends up giving me 1 over y squared. And pz, since there are no z's, this is just going to end up equaling 0. Now we go to q. We look at q, and we're going to need qx and qz as well, because q is like my y component. So I'm going to need the other two partials. Okay? So qx is going to end up equaling 1 over y squared. And qz, once again, is going to end up equaling 0 because there are no values for x there. There are no values for z inside of our function for q. And now r is like our z component. So we're going to need rx and rz. Okay, or rx and ry, the other two variables. Rx is going to end up being 0 because there are no x's and 2z minus 1. And ry is going to end up equaling 0 as well because there are no y's. So there we go. We end up having, there ends up our partials, or sets of partials. So what I want to do now is I want to notice I'm going to have x, right? Okay, this is my xy. So py has got to equal qx. Okay, py has got to equal qx. And so I look, and actually they are. 1 over y squared equals 1 over y squared. So check. That works. Okay. Now pz is like is going to be with respect to x, so that's going to have to match up with xz. Okay. So we're going to need that pz equals rx. All right. And so that's 0 equals 0. Right. Notice x and z, those two have to match up. When we talk about potential functions, it's going to become clearer as to why that's going to be the case. But for right now, we just kind of want to think about we're matching up, the variables. Next up, we're going to go over to, we already did qx. We now need to look at qz, so that's the yz. So yz is 0. So qz has to equal ry, because that's yz as well. And that's 0 equals 0. And that's all of our different pairs. And if you notice, check, check, and check, the three that we need, they're all equal to one another. Okay? So f is conservative. That is a conservative vector field, and that means that we are going to be able to find a potential function for this conservative vector field. Let's consider this one. Let's consider f of xyz equal to 2xyi plus x squared plus 2yzj plus y squared k. So I'll set down that p is going to be equal to 2xy, q is going to equal x squared plus 2yz, and r is going to equal y squared. So now what I need to do is I need to go in and I need to find py and pz. Py is going to end up equaling 2x, and pz ends up equaling 0. Right? Then I want to do q, and I'm going to have qx and qz. Those are the other two values, right? Remember, q is our y. So qx equals 2x, and that's just 2x. And then qz is going to end up equaling 2y. Okay? And then rx is going to end up equaling 0, and ry is going to equal 2y. So now we need to actually go in and make sure that the ones that we want to have match. So remember that x is like our p, so this we want it py and qx to match. So py has to equal qx, 2x equals 2x, check. Then we go in, we got pz. Pz's got to equal rx, right? xz, zx, and we end up with 0 equaling to 0, check. That works. And then also we're going to need that qz equals ry. qz equal to ry. Let's check if that's the case. We get 2y equals 2y. And then also, they also equal each other. So f is conservative. Once we developed whether or not f is conservative, we actually know that we can find a potential function phi. So the rest of this section, or this lecture that we're going to look at, is going to be us finding that potential function phi. And then our next lecture is actually going to be on using the fundamental theorem of line integrals in order to make integration a lot easier. Okay? Now what we want to do is we want to actually go out and find this potential function phi. So what we're going to do is we're going to say, okay, we're going to play off the fact that the conservative vector field f is equal to the gradient of phi. So what that means for us is that phi of x is going to equal 2xy. That's that value right there. Phi of y equals x squared plus 2yz. There's that. And the phi of z is going to equal y squared. So there's y squared. Now, what we're going to do with that is we've got a process. And the process is basically going to be, we're going to retrieve the parts of phi based upon its partial fractions. Or, excuse me, its partial derivatives. So we're going to start out with, we're going to take the integral of phi of x dx. Okay? And that's going to equal the integral of 2xy dx. And that's going to end up equaling, okay, that's going to end up equaling x squared y. And then it's going to be plus a function. And this function is going to be g of y and z. So it's going to be a function of just y and z. And the reason we know that we have that is because when we took the derivative with respect to x, right, d dx of this whole thing right there, okay, zeroes out the g of yz and leaves us with 2xy. Okay, so basically we need to retrieve that function of y and z. Okay, so now I've taken that derivative, and this thing here, this is actually phi, right? It has an unknown piece, but it is phi. So what I'm going to do now is I'm going to take phi of y. So phi of y, and that's this thing now. Now we know that that's the case, and so that's going to be del y of x squared y plus g of yz. Okay? And that's going to end up equaling then x squared plus, and we'll call this just gy. G with respect to y. And that equals phi y. Well, we also know that this thing here equals phi y. So phi y equals x squared plus gy, which equals x squared plus 2yz. A little algebra will then tell us that gy is going to equal 2yz. Okay, so xy is going to end up giving us 2yz. Awesome. Very, very good. Okay, so now what I need to do is I'm going to need to take the integral of gy with respect to y to give me back g of yz, right? Because I need to find g of yz. And so how I'm going to do that is I'm going to integrate this derivative. So I'm going to integrate 2yz with respect to y. And that's going to end up equaling y squared z plus some function with just respect to z. if I end up adding that to x squared y, okay, so I add it to x squared y, then that's going to end up being the entirety of phi. So phi ends up equaling x squared y plus y squared z plus some function of z only. Okay, so we end up having some function of z only. We'll need to figure out what that is. All right. So what I'm going to do is I'm actually going to take phi of z. Phi of z, which is that q function, or that r function. So phi of z is going to end up equaling del z of x squared y plus y squared z plus h of z. And so that leaves me with just y squared plus h prime of z. So I've got y squared plus h prime of z. And we notice that that's also phi of z. So we're going to compare now. So we get phi of z is going to equal y squared, which equals y squared plus h prime of z. And what that means is that means h prime of z equals 0, right? Because the y squareds will end up canceling and end up with 0 here. So you get h prime of z equals 0. So now we want to find that last function. We'll integrate 0 dz. Integrate with respect to z, okay? Which is phi of, excuse me, not phi of z, but 0 dz. That just ends up equaling some constant c, okay? And there we go. We're going to put them all together now. So we start out here, we've got phi. It's x squared y plus g of yz. So I've got x squared y. So this is phi of x, y, z. I've got x squared y plus, and then g of plus y squared z, that second part, plus some constant c. And that is my potential function. Okay? It gets easier. Harder to explain than it looks, I have to tell you. But it gets easier to actually kind of like calculate. It becomes very systematic. So why don't we do another example? Let's go in and look and find our potential function now for this vector field. We already know that it's conservative. We actually proved that this vector field was conservative. So let's take, we're going to know that we call this phi of x is going to equal negative 1 over y. Phi of y is going to equal x over y squared. And phi of z is going to equal 2z minus 1. So the first thing that we're going to do is we're going to integrate phi of x dx. So that's the integral of negative 1 over y dy, or excuse me, dx. Okay, and so this ends up equaling negative x over y. Plus, and remember we have that, that function g of yz. So we're going to take our integral of phi of x dx. Okay, then the next thing we're going to do is we're going to take del y, okay, and this is phi, so del y of phi, okay, and so we got del y of negative x over y plus g of yz, and this is going to end up equaling x over y squared, so that's the derivative of negative x over y with respect to y, plus we'll call this g of y. Okay, so plus g of y. And then we're going to compare, and this, by the way, is going to end up equaling phi of y. We're going to compare our phi of y's. We'll call it that. So we're going to take x over y squared plus gy and equals x over y squared. So what we can see there is that g of y is going to equal 0. Okay? Plus some, or excuse me, yeah, there it is. So g of y ends up equaling 0. So now I'm going to integrate phi of, or g of y, with respect to y. So I get the integral of 0 dy. And that's going to end up equaling, it'll be a constant, but it'll be plus h of z. So there's still a function of z that's left over there. Okay, so we've got the constant part. The constant part is going to be the thing that just has y's in it by itself. But then we also have our h of z. So now I need to take, and by the way, yeah, there it is. So now I need to go in and I need to find h prime of z. Okay? Well, h prime of z is going to equal phi of z. All right? And that's going to equal 2z minus 1. So h prime of z ends up equaling 2z minus 1. We're going to compare h prime of z to phi of z. That's our last piece. And then we need to integrate with respect to z. So we're going to integrate 2z minus 1 dz. So we'll integrate h prime of z dz. And that ends up giving me z squared minus z. Now what we need to do, we need to combine combine phi. First part of phi was our x over y squared, or excuse me, our negative x over y. That portion right there, that's from phi. So negative x over y. We have a constant here, which is the y part. We'll deal with that later. Plus z squared minus z plus c. And that is our potential function. So if we look process-wise, what did we do? We integrated our phi of x, okay, with respect to x. Then I took the derivative of phi, my result there, with respect to y, and I compared that to phi of y. I ended up with x squared, y squared, x over y squared plus g of y. That was equal to xy squared, and that ended up giving me g of y equals 0. So the comparison ends up giving me this function of yz. Then I take the integral with respect to y of my g of y, and so that's the integral of 0 dy, and that gave me a constant plus, don't forget you're going to have a function of just z in there. So that function of just z in there is important because we're going to need to retrieve that too. We take the derivative of h prime of z, it turns out, or yeah, we take the derivative of actually the whole thing. With del z of c plus h of z. And that gives me, in this case, h prime of z equals phi of z. Okay, so h prime of z equals 2z minus 1. And once I find that, then I take the derivative with respect, or excuse me, the integral with respect to z. Okay, that integral with respect to z was z squared minus z. Finally, I combine all of my pieces together. Basically, my x's, my y's, and my z. My x's, my y's, and my z's. We put them all together, and that gives me my potential function. Let's actually just confirm something. We'll show that the gradient of phi, okay, equals f. So we'll start out with phi of x, okay, and that's just negative x over y. So that's going to end up being negative 1 over y. Phi of y is going to equal, well, we got the derivative of negative x with respect to y, that's 0. Then we have minus x times 1 over y squared. So we get plus x over y squared. And then phi of z is just 2z minus 1. And so what you can see is that we, in fact, retrieved our potential function. We got negative 1 over y is phi of x over y squared is phi of y, and phi of z is 2z minus 1. And that is our potential function. Let's take a look at an example. Let's do it in 2 dimensions. Easier process. All right, let's suppose now that we have f is equal to 2xy cubed, 3x squared y squared plus cosine y. We want to now find the potential function. We actually already proved that this was a conservative vector field. So consequently, now what we need to do is we need to go in and we need to, in fact, just retrieve our potential function. The process is going to be very similar, but there's like 3 fewer steps, essentially, what's going to happen, because we only need to retrieve an x part and we need a y part. We don't need to retrieve the z part. So we got the x and the y. So my phi of x is going to equal 2xy cubed. My phi of y is then going to be 3x squared y squared plus cosine y. So I'm going to start out just the same way as I did before, phi of x dx. So that's going to be the integral of 2xy cubed dx. And that's going to then equal x squared y cubed plus some function of y. No z's, so it's just going to be a function of y. We'll call it h of y. And that's going to be phi. Now I'm going to take the derivative. I'm going to del y of phi, this phi that I found. So that's going to be del y of x squared y cubed plus h prime, or h of y. And that's then going to be 2x, or excuse me, x squared times 3y squared plus h prime of y. No further variables, so we don't need to like have a z. There's nothing that's needed there. We're just going to have our h prime of y. And so now I'm going to compare that. I'm going to compare to phi of y, because that is, in fact, phi of y. So this is 3x squared y squared plus h prime of y. And that equals 3x squared y squared plus cosine y. So when I go, I just notice that those two, they're the same. So I get h prime of y equals cosine y. And now I need to take the derivative, right? I've got my comparison. I'll take the derivative of phi of y dy, or excuse me, h prime of y dy, pardon me. So we take the integral of cosine y dy, and that just equals sine y plus some constant c. So our phi now, by the way, and we can just drop off the c. The c is going to drop off, but phi is going to then equal, it'll be the x squared y cubed, right? That's the part of that we have there for phi. So I got x squared y cubed plus sine y. And that is my potential function. Could there be a c? Yes, there could be. Oftentimes what you'll see is we'll just set this equal to some constant, and then it'll, that'll wrap up what we need. Okay? Notice phi of x is going to equal 2xy cubed, and phi of y is going to equal 3x squared y squared plus cosine y, which are both of our original values in the vector field. Okay? Let's take a look at one more example. Let's now prove that f is conservative, and then we're going to find phi. So let's say, for example, we got f of xy is equal to 12xy and 6x squared plus 6y squared. Essentially, that's it. So we're first going to prove that phi of y, okay, or not phi of y, this is p, so p of y is going to equal 12x, and q of x is going to equal 6 times 2x, which equals 12x. Okay? So consequently, the two of them are the same. py equals qx. We need those two to equal each other, so f is conservative. Now I need to go in and I need to retrieve my potential function phi. So I'm going to take the integral of, in this case, 12xy dx, and that's going to end up equaling 6x squared y plus, and then some function of y, h of y. Now I'm going to take del y of 6x squared y plus h of y, and that's going to end up equaling 6x squared plus h prime of y. I'll make a comparison then to my my q, right? Or my phi of y. So this is going to equal q. So I've got 6x squared plus, and this is just 6y squared, equals 6x squared plus h prime of y. So 6y squared is going to equal h prime of y. Now I need to go figure out what h of y is, to actually take the integral. So I take the integral of h prime of y dy, and that's going to equal the integral of 6y squared dy, which equals 3y cubed, or excuse me, 2y cubed. Now I just got to put them together. So phi, my function, is going to equal 6x squared plus 2y cubed. And there's my potential function. Just to check, phi of x, excuse me, 6x squared y, it's this one here, 6x squared y plus 2y cubed. Phi of x is going to equal then 12xy. Phi of y is thus going to equal 6x squared plus 6y squared. And we in fact have found the right potential function. All right. One thing to notice, mistake that I made just a moment ago, but to just clarify, remember that like essentially your x part is going to come up here. It's the product of the integral, the first integral, because this is phi. This is a derivative. Okay, that's a derivative right there. So consequently, it's not going to be part of your function. That's not phi. Okay, so you want to make sure that you go up to basically your first step here to retrieve that first part of the function. Then you'll notice as well, this thing here, this is actually h of y, if we wanted to get into that. Okay, we're going to add in the h of y piece. The two of those put together, they give us phi. So that basically finishes up our lecture here on conservative vector fields and finding potential functions. Doing this is going to come in very, very handy for our work with working with the fundamental theorem of line integrals. Okay, so first, confirm that you are looking at a conservative vector field and then attempt to find a potential function. This is a note of warning. If you are not working with a conservative vector field, you will not find a potential function because the relationship is wrong. Okay, so make sure that you are working with a conservative vector field first.